Dr. P here. In this video, I want to talk about this Carnival ride where it spins really fast and the floor drops out and the people stay stuck to the floor. This is a ride at Coney Island here, and you can sort of see these people. Some of them are having fun. They're upside down. All right. So the first thing we need to do to figure out the physics of this problem is to draw a picture that really makes sense. So instead of this picture sort of at an angle from above, we're going to look at this from the side. So here's our cylinder and the axis of rotation, and it's going to spin. So our person will be stuck to the side of this ride. All right, why are they stuck? Well, the first thing, you draw a picture. Second thing, draw a free body diagram. So when I look at the forces acting on this, we have the force of gravity going downward. There has to be a force upward because the person is not accelerating downward, and that force that keeps the person stuck to the wall is actually the force of friction. The force pointed inward is the normal force. And so the person will feel a force on the wall as they're rotating around. This normal force, if we sum the forces in the radial direction, we get just the normal force. That is going to be the centripetal force. All right. This problem you'll find, and they'll ask for a multitude of different things. In this, it's asking what is the angular velocity of the ride, assuming that the radius is r and the coefficient of static friction is mu. And so we are looking for how fast it spins around, or omega, the angular velocity. All right, we're partway there already, saying that the centripetal force is equal to the normal force. So that gives us mass times the centripetal acceleration is the normal force. Now, this is probably you might be at the point where you're skipping steps. So this gives us mass times the tangential velocity squared over the radius equals the normal force. Now in this problem, it doesn't ask for the tangential velocity, it asks for the angular velocity. And you might have the centripetal acceleration equation for angular velocity memorized, or you might not. Remember that the tangential velocity is just r omega. When we substitute that in for the tangential velocity here, we get mass times angular velocity squared times the radius is the normal force. All right, at this point we're stuck. We have no idea what the normal force is, and so we need to sum the forces in the other direction. When you get stuck, that's the next thing you do. So I've summed the forces in the radial direction, and now I need to sum the forces in the up and down, or the y direction. So the sum of the forces in the y direction is the force of friction minus the force of gravity. Now, as I said earlier, it's not accelerating. These people aren't accelerating up and down. And so that force, the sum of the forces, will be equal to 0. So we get mass times gravity, the force of gravity, equals the force of friction. Now we can substitute in our equation for the force of friction as just mu times the normal force. In this case, it's static friction, mu sub s, times the normal force. And then we can just divide both sides by mu sub s to get our normal force is equal to mg over the coefficient of static friction. So we can take this equation then and plug it in right here for the normal force. So we get m omega squared r equals the mass times the gravitational field strength over the coefficient of static friction. Our masses cancel, and in this case we're solving for the angular velocity, so omega is the square root of our gravitational field strength over the radius times the coefficient of static friction. That was really fast, but just remember what you do. Draw a picture, draw a free body diagram, sum the forces in the radial direction. Then you use Newton's second law. That's this guy. The sum of the forces in the radial direction is the centripetal force, which is mass times the centripetal acceleration. Then after that, we solve for what we can, plug in tangential velocity for centripetal acceleration or angular velocity for centripetal acceleration. When you get stuck, sum the forces in the other direction.